So welcome by the League of Ligands. We're going to talk about ligands a lot today because obviously a nanocrystal is partly an inorganic object, and you can look at it under TM, see all the different atoms of the core, but there is also this layer of organic molecules on the nanocrystal surface that is very, very important. That actually makes or breaks the core. And here is a famous example of where it was shown that just based on the amount of ligands that are on the surface, you can either completely quench the photoluminescence or restore this photoluminescence on cadmium selenide. So that's what we're going to talk about today, nanocrystal surface chemistry. Of course, like Quinten said, we're going to talk a lot about NMR, but not just about NMR. First, I actually want to start with a little bit about colloidal stability. What makes nanocrystals soluble? I think there's been very interesting work that has been published in the last 5 years that is worth some attention there. And then we're going to talk about NMR spectroscopy as a tool to look at which ligands are bound and which ligands are not. And then afterwards, I'll talk here about, I should, annotation, yes. Okay, then we talk about kind of the language that we use to describe surfaces. How can we formalize? How can we classify them? And then this formalization, once you have a language, you can start to talk about these things. You can start to predict what's going to happen. And finally, this is something very interesting. And from the last few years, we're starting to get insight in the thermodynamics of ligand binding. And so that's the last part of today. So first we start with colloidal stability, and we're going to start with a classical colloid theory from many years ago. And so here we have a figure from the original paper of Hamaker that was studying the interaction between two spheres. And he was looking at the attraction between those spheres caused by van der Waals interactions. And basically he solved the math behind this. And after solving the integral, he got something like this, which depends on the diameter of the two spheres and also the interparticle distance. And there is here this constant, which now we call the Hamaker constant, which contains elements such as the polarizability. So that is, in typical colloid theory, what we have to fight, because nanocrystals do not want to stay apart. They want to come together, they want to aggregate. And because there is this van der Waals interaction, this London attractive forces bringing them together. So what is keeping them apart? And note, I didn't say that in the beginning, but I'm going to mostly focus here today on organic ligand stabilized nanocrystals. And so there's a whole class of inorganic stabilized nanocrystals, but that is well, the theory there is completely different. And so here, and we can also not use solution NMR to study that. So today we're only talking about these organic ligands. Okay, so we have attractive forces. We need repulsive forces to make sure that they don't come together. And that's why we add those. Oh, what is happening here? Oh, there. That's why we add here these long steric ligands on the nanocrystal surface. If now two nanocrystals want to approach, there is this ligand shell that is in between the two nanocrystal surfaces. And so if you force those two close together, you will start to compress this ligand shell, and you're paying a price for that. And so this is a repulsive force that has been kind of quantified with this very complex expression here, which depends on sigma, which is the ligand density. So the more ligands there are on that nanocrystal surface. There are some other effects that happen too, which is ligand intercalation, which if they nicely slide into each other, then there is some gain in enthalpy, but loss in entropy. Also, when nanocrystals come together, ligands can, for example, desorb, and then you lose your colloidal stability. So let's look a little bit more in a visual way of how nanocrystals can precipitate or flocculate. And so if you sum up all those energetic contributions, attractive, repulsive, then you can arrive at graphs like this. So obviously, if you bring them too close together, then the energy will go extremely high up because you can't force atoms into each other. So that why you have this very steep repulsion here on the left side. If nanocrystals are very far apart, they're not interacting, and so their interaction energy is zero. That's what we see here. This is the interaction energy based or dependent on the interparticle distance. And then if you see that nanocrystals come closer and closer together, so the interparticle distance decreases, then we start to see a minimum here. And the extent of that minimum, so the depth of that potential well, depends on the size of the nanocrystals. So here we have a 3 nanometer nanocrystal with a ligand that's about 1 nanometer in length and a ligand density of about 3 ligands per square nanometer. It has a very shallow potential well. And so with thermal energy, you can easily escape from that potential well. With a 5 nanometer particle, it becomes deeper, and with the 7, it becomes pretty deep. And so this theory, this classical colloid theory, predicts that 7 nanometer particles with this particular ligand or this ligand length, they will precipitate because they will find their thermodynamic minimum close to each other, and they don't want to be far from each other. Okay, let's look at a bit of the other variables. Here, we have a fixed nanocrystal diameter, 5 nanometers, fixed ligand coverage, but we're changing the length of the ligand. And you see for about a 1 nanometer long ligand, you have quite a deep potential well, but then the longer your ligands become, the more shallow that potential well becomes. And also the farther away, you will find that minimum at the interparticle. And so the interparticle distance, you see that the minimum appears at larger and larger interparticle distances. And that's of course because the ligands are longer. And so as soon as they touch, they will start to compress, and there will be the equilibrium. Also, ligand coverage has an effect, but it's not very important unless you go to really low ligand densities. And that's what this right figure is showing you here. And so the difference between a ligand density of 1 or 3 per square nanometer does not really change this potential well a lot. But if you then go to 0.2 ligands per square nanometer, then you really start to get deeper in that potential well. And so this is basically classical colloid theory. It's saying the longer the ligand, the better, the more ligands per square nanometers, the better, and the bigger the nanocrystal, the heavier the attraction, and so the easier they will precipitate. But then Jia Peng published some very interesting work in 2016 talking about nanocrystals as soluble species. So then we were not talking anymore about a kinetic stabilization of this colloid that was not in thermodynamic equilibrium. No, Jia Peng regarded these nanocrystals as small or as big molecules. He applied the same principles as we can apply to a small molecule. And he just said, well, an nanocrystal is a big molecule. And it also has an equilibrium solubility. And this equilibrium solubility depends on the nanocrystal size. And it decreases with the nanocrystal size. So what characterizes this precipitated state? That means, or in the precipitated states, the ligands are ordered. They are nicely crystallized. And so you can think here about, let's say, octadecylphosphonic acid as a ligand. So a long saturated chain. In the precipitated state of these nanocrystals, the ligands are crystallizing on this nanocrystal surface. Now, once your nanocrystals dissolve, then in the dissolved state, all those ligands will get conformational flexibility. So you're gaining a lot of entropy in this process, but you're losing enthalpy because you have to give up the crystallization enthalpy of those ligands on the nanocrystal surface. And so that was his main realization, that this is an entropically driven process, that if you can make sure that ligands cannot crystallize, then they will have a much higher solubility, because then you destabilize this precipitated state. And that's exactly what he showed with these branched ligands, which he called entropic ligands. And with a common, he said, common ligand is the stearic acid, for example, carboxylic acid, C18 chain, and that crystallizes very well. And so how can you stop it from crystallizing? By adding branching points. And by only adding one branching point here, you really catapult the solubility from very low to very high. And this is orders of magnitude. Note, this is a logarithmic scale. Now, I have a lot of respect for Jiagong Pang, and I find this an amazing paper. I disagree with one thing, and it's to call stearic acid a common ligand. For me, the most common ligand would be oleic acid. But of course, oleic acid does not provide such a stark contrast with these entropic ligands, because oleic acid is an entropic ligand, and because this double bond, this cis double bond, it cannot really crystallize well on an nanocrystal surface. And by design, oleic acid is an entropic ligand, which is exactly why people love all ligands with oleol, oleolamine, oleoyl phosphonic acid, oleic acid. They all work very well because of the fact that they are entropic. And then another group that did fantastic work was the group of Todd Krause. And he looked with simulations where every atom was given a separate, well, was explicitly modeled, also the solvent. And he saw these kinds of pictures. So every atom of the solvent or every molecule is being modeled exactly. Here you see gold nanocrystals with, for example, hexadecane thiol ligands. And he saw exactly the same thing, that ligands crystallize on the nanocrystal surface in the precipitated state. And then when ligands do not crystallize anymore, if you increase the temperature, for example, and you melt the ligand shell, then they become soluble. But in the precipitated state, ligands crystallize. And they don't just crystallize, or the result of that crystallization is that they form bundles on the surface. Ligands start to aggregate on the nanocrystal surface. And that creates regions on a nanocrystal where there are a lot of ligands, and regions where there are not a lot of ligands, like here. And then nanocrystals can find each other and can like lock in place. It's a bit like DNA with a small groove and a minor groove. So here you have, in these ligand shells, some grooves exist. And here what this picture is showing is one nanocrystal filling up the groove of another nanocrystal with a ligand bundle. And so here again was shown, yes, crystallization of ligands on nanocrystals is what's driving precipitation or dissolution for small nanocrystals. And this was a very interesting contribution, because they exactly gave the point where nanocrystals behave like small molecules with an equilibrium solubility, and where the ligands determine whether, where the crystallization of the ligands determines the solubility. And so that's the point where they behave like molecules to the point where they behave like colloids. And that's what this figure is showing here. These are all gold nanocrystals. And here it's shell dominated. This comes from the simulations where they see that the nanocrystals start to precipitate because of the ligands that are crystallizing. So this is what they call shell dominated. I consider this okay. Here I can see nanocrystals as having a solubility, as behaving like small molecules. And here, when the nanocrystals become bigger, they start not to precipitate because ligands crystallize. No, they precipitate because the core van der Waals attraction becomes too high. And so here you really see the point in between. So the point is for gold nanocrystals around, let's say, 8 nanometers. Below 8 nanometers, it behaves like a nanocrystal. above 8 nanometers, it behaves like a classical colloid. And I've put here a few of Todd Krause's papers that I found very inspirational and that describe this in more detail. Okay, that was about solubility. And so how can we maximize nanocrystal solubility? Let's now come to my favorite subject, NMR spectroscopy. And so I will explain you 3 tools that we have to look at nanocrystal surfaces. The first one is this, just a 1D, very simple 1D NMR spectrum. Second one is a bit more complicated. It's called DOSI. It's diffusion ordered spectroscopy. It's an NMR technique in which we can measure the diffusion coefficient of a molecule or of a molecule that is bound to a nanocrystal. And the third one is NOESY. It's nuclear Overhauser effect spectroscopy. And it's a 2D NMR technique where we can look at the sign of the cross peaks to find out whether a molecule has bound behavior or not. Okay. Let's start with the 1D spectrum. And with this very fundamental question is, why are these ligand broadened? So we know that when ligands are free, they have these sharp resonances with fine structure. You can recognize triplets, quadruplets, quintuplets, etc. And then as soon as a ligand binds to a nanocrystal, here is oleic acid, everything starts to broaden. And this is a typical spectrum of an oleal-based ligand bound to a nanocrystal. And so now the question becomes, why? And so there are basically 2 mechanisms in NMR, and that's homogeneous broadening and heterogeneous broadening. The first thing I want to show you is that this broadening is also is not characteristic for the molecule, it's characteristic for the resonance. Because resonance 6 here in the methyl, which is the farthest away from the surface, that's the sharpest. Then we have the alkene resonance here about in the middle. It's already somewhat broader, and you also see this in the full width half maximum. This is only 36 hertz. This is already 70 hertz. And we could not even measure it for resonances 1 and 2, which are very close to the surface, and they are so broad, they're about here, but we can't really measure them because their width is so large. And so one reason is homogeneous broadening. And homogeneous broadening depends on the mobility. And so when you have a small molecule, it is very mobile, it can tumble around, has a lot of rotational mobility in the solution. And that yields those narrow lines. But once something becomes big, it starts to rotate much more slowly, and that creates a faster T2 relaxation, and that leads then to broader lines. Now, the flexibility or the conformational flexibility can depend on the position of a chemical moiety. So if you're very far from the surface, like this methyl group here, it has a lot of rotational mobility. The ones here very close to the surface do not have that. And so that's one part of the broadening. But if we calculate how much, because you can measure the T2 time, and so you can calculate the homogeneous broadening, then you see that this homogeneous broadening is only a small fraction, and so here it's 9 hertz of the total full width half maximum. And so most part of the biggest contribution to the broadening of these resonances is heterogeneous broadening. And that means that this one resonance here is not one resonance that is broadened. No, it is a superposition of all kinds of different resonances which are broadened, but all these different resonances have slightly different chemical shifts, meaning they have different chemical environments. And that is because of the poor solvation of a ligand shell. And imagine a ligand alone in the solution. It is perfectly surrounded by solvent. And then you imagine another ligand in the solution. It is also perfectly surrounded by solvent. So they're exactly the same. And you see a perfect, on the same chemical shift, you see them appear. But now those ligands start to bind to a nanocrystal surface. And on that surface, it's crowded, and they can start to feel the other ligands. So that means they have a slightly different chemical environment. And then it depends, how good is the solvent penetrating in that ligand shell? How good is the ligand shell swollen with solvent? And the more solvent inside that ligand shell, the more homogeneous it's going to be. But if solvent is being excluded from the ligand shell, there's going to be a lot of ligand-ligand interactions. And so there's going to be a lot of heterogeneous broadening. So let us look at an example. And so here we change ligands a little bit. So here we have another model system. And these are hafnium oxide nanocrystals with this little polar ligand on the nanocrystal surface. And you also see the TEM here, they're quite beautiful nanocrystals. But if we now look at their proton NMR spectrum in different solvents, we see that the line width is very different in those different solvents. And if we try to find a correlation between solvent properties and the full width half maximum of those lines, we arrive at something like this. So you can try to make a correlation with the viscosity, but that doesn't really work out. It is very much correlated with the hydrogen bonding parameters as defined by Hansen. And that's now logical, because now you can look at this ligand and see, okay, this has a lot of oxygens, it's kind of polar, and it likes hydrogen bonding. It's a hydrogen bond acceptor. And so the better the solvent is at donating hydrogen bonds or at providing hydrogen bonds, the better the solvent will be able to swell the ligand shell. The better the solvent will be able to penetrate the ligand shell. And so here you have an example of, we have a polar hydrogen bond demanding ligand. So the most narrow lines you will find in a solvent in which it is very well soluble, in which provides these hydrogen bonds. Okay. Now let's go to the influence of the nanocrystal size on this broadening. And here we go again back to the oleic acid ligands that we know. And so this here is the alkene resonance of oleate bound to lead sulfide nanocrystals of different sizes. And here is the full width half max plotted in function of this core size. And you see the total broadening just continues to increase. Well, you also saw that from the NMR spectrum. But what we then did is again disentangle these contributions. We said, okay, measure again the T2, calculate the homogeneous broadening, subtract the homogeneous broadening, and then get the heterogeneous broadening. And then you see the areas here evolve, and you see that the homogeneous broadening continuously increases. That's logical. Homogeneous broadening was related to size and rotational mobility. So bigger nanocrystal has lower rotational mobility, and so the homogeneous broadening increases. This heterogeneous broadening initially increases and then levels off. That's because lead sulfide becomes faceted after a certain size, which is probably around like 6 nanometers. And so if a nanocrystal is faceted, that means the curvature is 0 on those facets. Now in a nanocrystal with a very high curvature, the ligands are all pointing away from each other. There's a lot of space in between for solvent to penetrate. Now, if that curvature starts to become smaller and smaller and smaller until it becomes flat, now on a flat surface, all the ligands are neatly stacked next to each other and there's no space for solvent. And so you see that once the curvature is decreasing, you're actually increasing the heterogeneous broadening. You're increasing the ligand-ligand interactions. But of course, as soon as you have a flat surface, because you have a faceted nanocrystal, further growth of the nanocrystal is not going to change the heterogeneous broadening. Okay, then one more thing is the choice of your solvent has an influence of where the bound state appears. So here we have cadmium selenide or hafnium oxide in either toluene or chloroform. And in an aromatic solvent, you nicely separate the bound from the free state. That's because there is an aromatic solvent-induced shift that exists. So this is a nice little trick to neatly separate free from bound species. Then I've only been talking about proton NMRs, but we can also do phosphorus NMR. So here we have zirconia nanocrystals synthesized in topo, right? Trioctyl phosphine oxide. Now we have a phosphorus in our ligands, so we can do phosphorus NMR. And there it's very broad, so you need lots of scans. You can't do just a regular phosphorus spectrum. You have to have high concentration of nanocrystals and do like 3,000–4,000 scans. So that's usually an overnight measurement. And then you see these very broad resonances belonging to bound phosphonates or bound topo, depending on the ligand shell of your nanocrystals. So that was 1D, right? So there's a lot to say about 1D NMR, and there's a lot of information to extract there. But now we go to a bit more complex NMR techniques. First one is dosing. So in NMR, you apply a high magnetic field to your sample, and that magnetic field is very homogeneous over your NMR tube. And that means that it doesn't matter where the molecule is, they all have exactly the same frequency in the NMR spectrum. Now in dosing, we're going to destroy that homogeneity. We're going to add another magnetic field, which we call a gradient, because that magnetic field depends on the Z position. So that's why it's called a gradient, because it's a magnetic field that is dependent on the position. And that means now that every molecule, depending on where it is, will have a slightly different frequency. So what's the consequence of that? That means if we now, remember NMR, magnetization, you first excite it, you put it in the XY plane, it starts to precess, but now every single one is going to precess with a slightly different frequency. And if you wait a little while, then they're all at such a different speed that you will completely destroy the coherence of that signal. And you have zero signal left. Okay, does not sound very useful. But now we come to dosing. What if we apply first a gradient, then wait a little bit, and then apply the opposite gradient? And then it first all goes in one direction, and the spiral goes in one direction. You apply the opposite gradient, and so it goes back in the other direction until it perfectly refocuses back to your coherent signal, which we can measure. But of course, it's not a perfect experiment. This would be if you get perfect refocusing. But refocusing is not perfect, because in this time that you're waiting, there is actually, so in this time that you're waiting, molecules are moving position. And so if they would remain exactly where they were, this whole trick would work. But since they're moving, the opposite gradient that they feel is not exactly the same as the initial gradient. And so you don't refocus perfectly. And as a result of that, you see a lower intensity in your spectrum. And that is something we can use, because now depending on the strength of this gradient, the length of this gradient, or the time that you wait between the two gradients, you will see a stronger decay. And that is what we use in dosing. Dosing is actually a pseudo 2D experiment where we measure 1D spectra, with the only difference between them is how long or how strong the gradient was. We don't change times in NMR. Times are complex because there is also relaxation happening. So we fix the diffusion time, we fix the gradient length. The only thing that we change is the gradient strength. And that's the difference between all those curves here. And here I give an example of a solution in a solvent, which is TFA, so trifluoroacetic acid, of this polymer. So TFA is a small molecule, the polymer is a big molecule. And then you see that this decay is faster for the small molecule and slower for the big molecule. That's because this small molecule changes position much more quickly. It diffuses much more quickly. And here is the equation that actually relates the intensity that you see after a certain gradient strength after a certain gradient length, etc. So if we now change this equation a little bit and plot the intensity, for example, of this resonance, we just take all these points and we put them in one plot where we plot the natural logarithm of the intensity versus the squared gradient strength. If you look at this equation, then you see that indeed this should be a straight line. If there's a single species there diffusing, it should be a straight line. And all the variables in this equation are known except for the diffusion coefficient. So if we, this is the red, if we fit that data, we get the diffusion coefficient. And then there is the Stokes-Einstein equation, it's this one here, which is relating the diffusion coefficient to the size of the hydrodynamic size or the solvodynamic size in another solvent than water, it's solvodynamic, in a solvodynamic diameter of your object. So think now about a nanocrystal capped with ligands. So if you measure the diffusion of a bound ligand, you get the diffusion coefficient, you turn this into diameter, you're going to get the diameter of the nanocrystal core plus twice the ligand shell. And because there's ligands both on the left and on the right of the nanocrystal core. So this is the way that you fit a single resonance to get the diffusion coefficient. Now you can do that for all the resonances and then organize those resonances according to their diffusion coefficient. And that's then a typical 2D plot as what you see here. So in this is the 1D spectrum where there are all kinds of molecules, 3 different ones with different diffusion coefficients. And with those, we can separate those according to their diffusion coefficient. So here we see the ester. Here we see ethanol, and here we see bound oleic acid. And we can really disentangle those 3 contributions. And we have used that to, for example, detect polymerized octadecene in the presence of nanocrystals. Now, what if you don't have a textbook example? So what I explained to you is like, okay, when a ligand, like an oleic acid is tightly bound to lead sulfide, put it in the NMR, I see broad resonances, I take a dozy, and then I get exactly the solvodynamic diameter of this object. But what if, for example, you don't get a straight line in this ln of the intensity versus the square gradient strength? If you don't get a straight line, then there are at least multiple species in that region of where you're looking. So the resonance that you think is one resonance is not one, but they're actually a superposition of 2 with 2 different diffusion coefficients. Now this is a situation that often happens when you have still free ligand around. It appears, especially in chloroform, the free ligand and the bound ligand overlap. We don't have this problem in toluene or benzene, but in chloroform they overlap. And if you then take if you then look at the decay of the alkene resonance, for example, you will see not a straight line, but this curved line, which you can fit with 2 straight lines. So here you can fit then the slow diffusion coefficient and the fast diffusion coefficient. The fast one belongs to free ligands, and the slow one belongs to the bound ligands. Then you can also have non-spherical nanocrystals. That is also an option. And then you just have to know that the Stokes-Einstein equation changes a little bit depending on the shape of the object. And so you can calculate that for spheroids, for platelets, for spheres, or for cubes. So for spheres and for cubes, I put it here. Okay. On to the next NMR. The next NMR technique. This one is a bit too complex to explain what the theory behind is right now. But basically, proton nuclei of protons interact with each other not only through bonds, but also through space. And this is called the nuclear Overhauser effect. Now, this effect is different for small molecules. Then it's small and positive. than for large molecules, because for large molecules, it is negative and has a larger intensity. And that is something we can use in a 2D spectrum, which we call NOESY, nuclear Overhauser effect spectroscopy, where we see one sign. So this here, the color represents the phase. So it can be either positive or negative. Now, the diagonal per default is always negative. So if the color is the opposite as the diagonal, so here the diagonal is black, this color of this crosspeak is red, so that's a positive NOE. Let's go back here. Okay, when it's a positive NOE, then we are in the range of a small molecule. So yes, this is oleic acid that is simply not bound. But if oleic acid, for example, is bound to a nanocrystal surface, then you see the same color as the diagonal, and then you have these negative NOE crosspeaks, which means, yes, it is bound to a nanocrystal. Now you can say, why do we need NOESY? I mean, we have everything that we can possibly need in the 1D and the DOSY. And the 1D, it's broad, it's bound. The DOSY also tells us like exactly how fast it's diffusing. But what if your ligand is not tightly bound, but is in dynamic exchange coming on and off the surface? Then you're going to see an average in DOSY and an average in the 1D. And let's say that it's 90% free and only 10% of the molecules at all times are bound. Yeah, then the average in the 1D is going to be quite sharp. And in the DOSY, it's going to be quite fast. But NOESY is extremely sensitive. You can detect up to, this is really the pushing it, but up to 1% of the bound fraction. So if you have 99 molecules that are free, but one is bound, and those are exchanging, at all times there is one bound and 99 free, then the total signal of all those 100 molecules is going to be negative. And so that was very useful to look at perovskite nanocrystals, for example, which have a very dynamic surface chemistry. And so there it was useful to use NOESY to distinguish that, for example, pure oleic acid cannot interact with a nanocrystal surface. And you can see this red crosspeak here saying oleic acid is not interacting. While this ammonium here, this protonated oleoamine, with the counterion as a bromide, they could interact with the nanocrystal surface. Now, for the people saying, oh, oleic acid can interact with a cesium-like bromide, yes, true. If you add more oleoamine, then it becomes again an ion pair, and then it can bind to the nanocrystal surface, but not under its acidic form. Okay. Probably a lot of information, and that's what I'm going to try to summarize a little bit right now and to give you a bit of a playbook. You measure 1D, DOSY, and NOESY, and then you will be able to tell whether something is not bound, tightly bound, dynamically bound, or unpure. Let's look at those three examples. Not bound. Not bound means we see sharp peaks in the 1D. We see very fast diffusion, and we see positive NOE cross peaks. Tightly bound means very broad peaks in the 1D spectrum. Slow diffusion coefficient, and because the ligand is tightly bound to the nanocrystal, it diffuses with the nanocrystal. And also the NOESY gives you negative cross peaks, showing you it is a bound molecule. And then we have dynamically bound. Let's say 90% free, 10% bound. And the 1D, you're going to see the average, sharp. In the DOSY, you're going to see the average, but it's 90% free, so mostly quite fast. And it's only the NOESY that's going to tell you that this molecule is actually interacting with the nanocrystal surface, but in a dynamic way, not in a tightly bound, fixed way. Now, how do you know, or how do you see that your dispersions are unpure? Well, if you start out with sharp peaks in the 1D spectrum, so this is a bit of caricature because you see using the same spectrum for all these. If in principle, when you see free plus bound, you can still see a broad peak plus a sharp peak on top. But if you have a lot of free ligand, you're actually going to see something like this. In the DOSY, you're going to see not one straight line of one species. No, you're going to see that underneath this sharp peak, there's probably a broad peak that you did not see because there is this slow diffusion coefficient that belongs to that bound state. And then the overall nosy spectrum is going to be negative because all these things are interacting with the nanocrystal surface. So that's how you can distinguish those 4 cases with those 3 techniques together. Okay. I'm taking a 10-second break. How do we talk about nanocrystal surfaces? And here, for the people that know me and have read my papers, I'm going to take, this is how I teach my course at my own university. And you might be surprised because I'm going away from the LXZ formalism. So we have 2 models basically to talk about how ligands interact with nanocrystal surfaces. One is the covalent model that assumes that every nanocrystal ligand bond is a covalent bond, is a 2-center, 2-electron bond. And then we classify ligands depending on where those electrons are coming from. So if the ligand is donating 2 electrons, we call that an L-type ligand. If the ligand is donating 0 electrons, we call that a Z-type ligand. If it is donating 1 electron, we call it an X-type ligand. Small exercise. What is an amine? I know we have limited interaction possibilities, but maybe people can write in the chat. Where's the chat? Can they write in the chat?
Yes, they can.
Okay, so
not in the chat that you have on Zoom, but yes, on the chat that they find on the website.
Okay, that's not very useful. Okay,
not connected.
Then we just proceed, no problem. So oleamine is what I would call an L-type ligand. Right? It's a Lewis base. It donates this as this free electron pair with two electrons. This carboxyl is an X-type ligand. One thing that I didn't mention yet is that you have to classify these ligands in their neutral form. So you might be inclined to say carboxylic acid. Well, it's donating 2 electrons. It's a carboxylate. No, then you're trying to classify this ligand in its anionic form as a carboxylate. We actually have to look at how many electrons it is giving in its neutral form. And so a carboxyl radical, if you want, donates 1 electron to the nanocrystal ligand bond. And so a carboxylate is an X-type ligand. Aluminium trichloride is Lewis acid. That is having an empty orbital, and so that's a Z-type ligand. And now I also want to introduce you to the Ionic model, which is a bit more intuitive. Because here we just talk about neutral and charged acids and bases. And there is a one-to-one correspondence between the covalent and the Ionic model. So an L-type ligand is a neutral base. A Z-type ligand, that's a neutral Lewis acid. X-types, well, there are 2 kinds of X-type ligands. One that translates in the Ionic model in a charged base, like a carboxylate, interacting with a metal. Or one that translates into a positive acid, a positively charged acid. And here an example is a proton, because that's interacting with the non-metals on the nanocrystal surface. And so this Ionic model seems a bit more appropriate to describe nanocrystals, because this covalent model was described by Green for metal ligand interactions. It was not really meant for non-metal with ligand interactions. But a nanocrystal has 2 binding sites. It has both the non-metal and the metal on the surface. And so you actually also have to be careful talking about carboxylate and saying, well, that's an X-type ligand. Well, it actually depends on how it binds. If it binds like this, then it's an X-type ligand. If it binds via this X-type functionality here, but it's also additionally binding via its L-type functionality, this extra electron pair on the carbonyl, then it's an LX ligand. Typically, we're going to describe it as an X-type ligand because that's what we need for the charge neutrality. And but it's very possible that it binds like this. Now, this is a classification of ligands, but if we work in non-polar solvents, which we mostly do, then there's this charge neutrality requirement, meaning that the whole object, nanocrystal plus ligand, needs to be charge neutral. And that leads us to binding motifs, which is combinations of nanocrystal stoichiometries and the ligand type. For example, we have here this cadmium selenide nanocrystal, which is cation rich on the surface. So there is one extra cadmium atom on this surface. Well, it has to be charge neutral, but we're adding here a cadmium 2+. So this needs to be charge balanced by two X-type ligands. Or we can also have a neutral nanocrystal core, for example, hafnium oxide, neutral, with two X-type ligands. But one is bound to this oxygen and the other one is bound to the metal. So this could be a proton and this could be a carboxylate. Together, charge neutral. Or we have a charge neutral lead sulfide core with a charge neutral L-type ligand or an X-type ligand. And so here you see the duality is basically what do you define as the core and what do you define as the ligand. If you say cadmium selenide is cation rich, then X-type ligands are binding to the surface. If you say no, cadmium selenide is stoichiometric and it is actually cadmium carboxylate that is the ligand, the Lewis acid binding to the nanocrystal surface. It's an equally valid way to look at this, and it will only depend on what are the new ligands that you're giving this system, and that will determine how it will react. So cadmium selenide you can describe equally well via this way or via this way. Now, like I said, we can also do this with the Ionic model, which I start to prefer a bit right now, because it does not require covalent bonds. And then, for example, for hafnium oxide, you can argue that hydrogen, the proton, is having a covalent bond with the oxygen, but it's much harder to do with, for example, an ammonium ligand. And so this ammonium ligand is actually interacting with the surface. It's not just a counterion in the case of seasoned lead bromide. And there, so this is a hydrogen bond or an ionic interaction. And so here's the Ionic model a bit easier because you just say, well, we have a neutral, charge neutral core with a mixture of, or a combination of a charged acid and a charged base. Easy. Now these binding motifs are not just for fun that we're defining this. It's here you see the example of where we have the same ligand, the same X-type ligand is carboxylate, but a completely different binding motif, and thus also completely different reactivity. And so here it is charge neutralized by excess cations on the surface. Here the carboxylate is charge balanced by protons on the surface. And that has an effect on how these ligands can exchange or be displaced. I call it an exchange when we keep the binding motif the same. So if you just do an L for L exchange or an X for X exchange, the binding motif remains the same. And then there are these displacements where the binding motif changes. For example, again, you can look at this cadmium selenide as stoichiometric with cadmium carboxylate on the surface. Now you can remove that whole cadmium carboxylate unit with L-type ligands, which are Lewis bases. And so then you form this metal complex in solution and you have stripped the surface from its ligands and now other L-type ligands can bind. Or also this, this combination of charged acid and charged base or two X-type ligands, you can also displace with two L-type ligands. I had an example here from my own research, but I think I'm going to skip that in the interest of time. And then this one too. Yes. Because we still need to talk about thermodynamics. And if I'm right, we have only 10 minutes left. So the final part of this presentation will be about the thermodynamics of ligand binding. And I will already immediately start with saying that this is almost impossible. Because for thermodynamics, we want to define, for example, an equilibrium constant. And then we're defining a binding site, just like here, we have one binding site. We make a cartoon. We have one carboxylic acid, one cadmium carboxylate on the surface that is being displaced, forming this metal complex. And we're describing that with a single equilibrium constant. But a nanocrystal is a very heterogeneous place. I mean, look at it. Every single site seems to be almost different. And that is also reflected in its thermodynamics. So there is not a single equilibrium constant associated with this displacement, for example. No, there are multiple equilibrium constants, multiple of these displacement processes happening next to each other. And so that's very important before we start this section, is that you realize that the nanocrystal surface is also thermodynamically very, very heterogeneous. Okay. Now let's talk about how much space do we have on a nanocrystal. So this is a self-assembled monolayer on gold. It nicely stacks. And what is the conclusion here? There are about 5 of those, 5 of those thiol ligands per square nanometer on this gold surface. But there were 12 gold atoms per square nanometer available. So that means not every gold atom is receiving a thiol. And that's just because of space. I mean, this alkyl chain occupies space. You can't just push an atom in another one. And the only reason why nanocrystals sometimes you can go a bit higher than 5 ligands per square nanometer is because of the curvature, but not much. So a realistic ligand density is typically 3 to 4 ligands per square nanometer. And so sterics are a very important topic in nanocrystal surface chemistry. I give here an example of an X-type exchange where they started from, I think it was stearic acid, but I'm not sure. It could also be oleic acid. And then they added a new ligand, and this was the new ligand, hexadecanoic acid. And they just looked at the mole fraction in the solution and the mole fraction on the nanocrystal surface. And that was exactly the same. The surface had no preference for either of the two ligands. So this interaction between the ligand and the nanocrystal was the same for both ligands. Also, the ligand-ligand interactions were the same. But then they added this branch mark. In the theory of Peng's paper, it's like, yeah, these branch molecules should improve the dispersibility of the nanocrystals. But actually, it does not exchange because of steric problems. So you see here that the mole fraction on the surface is much lower than the mole fraction in the solution. And that's because this second chain here needs space. Now, again, we don't have to reinvent the wheel. There was a guy, Tolman, that measured sterical hindrance for metal complexes. And he defined this Tolman cone angle as a way of measuring how sterically bulky is a certain ligand. And then we evaluated that with L-type ligands, with different L-type ligands. So we have here cadmium selenide with L-type ligands, and we can do exchanges with them. And so we could evaluate which L-type ligand is a better ligand than another one. And then we had here a graph defining the cone angle on one side and the pKa of the associated acid on the other side. And so that means that this area here with a high pKa, those were very basic molecules. So a very high affinity for the surface in principle. But here at the top were also the ones with a very large cone angle, so that were very sterically hindered. And so we found here this area with good ligands, and only those were binding well to the nanocrystal surface. So they needed to have a small cone angle, so a low steric footprint, and a high basicity. And then we could, rank those ligands according to they don't bind at all, they bind really well. And there you can see that sterics are extremely important because this is a tertiary phosphine. Here here we decrease the bulk of those alkyl groups going from butyl, ethyl to methyl. Here in the amines, we go from a tertiary to a secondary to a primary amine. And it's really a big difference going from a secondary to a primary amine, for example. So those were the sterics. Sterics are extremely important if you want to exchange ligands. Another one that I want to discuss are proton-coupled exchange equilibria. And so these X-type ligands that exchange are always proton-coupled. You always add an X-type ligand as in its acidic form, and then some proton transfer has to happen. And so there was here work from both Hens and Dempsey showing that cadmium selenide capped with carboxylates exchange readily for phosphonic acids or easily for thiolates. And those are just very strong ligands. Now let's analyze an X-type exchange a bit more carefully and separate it in different thermodynamic steps. So the first one is the desorption of the X-type ligands. So in reality, this does not happen because this would make charged species and we're working in non-polar solvents. But this is a thought experiment. Desorption is the first step. Proton transfer is the second step. Adsorption of the second ligand is the third step. If you sum this all up, this is just an X-type exchange. And now what is found is that this proton transfer is often dominating. Because here, for example, if you have this equilibrium between hydrogen chloride on the surface and carboxylates on the surface, then the equilibrium is actually to the left. The hydrogen chloride is winning this fight. While chloride is in principle not a great ligand, carboxylate can bind chelating. It's much better ligand. But the chloride wins, and that's just because of this proton transfer step. And it is only when you eliminate the proton transfer step from the game, but for example, by adding a base, then it goes in the other direction. Then you see indeed, yes, carboxylate is a better ligand because it is going in that direction. But you had to remove this obligatory proton transfer step from the game. These are phosphonic acids, okay? 2 more minutes, okay. Finally, we come, what else influences ligand binding? It is multidenticity. And so here we again are talking about the Z-type displacement forming this complex here in solution. Well, if you do that with just a tertiary amine, it is not very efficient. Only 11% is displaced from the surface. Now, if you do that with the same moiety, this tertiary amine here, but you make it now into a bidentate ligand, you increase that efficiency to 90%. But maybe that's not really a good example. I mean, that's an example of where we're talking about multidentate ligands in solution, not really on the nanocrystal surface. Right? This is just regular metal binding multidentate ligands. So we started making these kind of multidentate ligands that were actually designed to bind the nanocrystal surface. And they do exchange for 2 oleates, but we didn't really pay very detailed attention to how many oleates are exactly being displaced by how many of these anthracene diphosphates. And so this is very recent work where we looked at tetradentate ligands. So based on this calixarine or resorcinarine scaffold, it's a resorcinarine with 4 phosphate ligands, and we had 2 versions of that. And then we started very carefully adding small amounts of ligand to nanocrystals with oleates. And in the beginning, we saw an almost 1-for-3 exchange. So one of these tetradentate molecules could displace 3 oleates. So it was almost binding, well, it was binding as a tridentate molecule. But if you started adding more and more and more, this slope of this reaction changed. And in the end, you almost needed half an equivalent to do complete exchange. But half an equivalent does not mean that it's tridentate. That's actually a bidentate behavior. And so here we saw a very important limitation of multidentate ligands. Is yes, they bind extremely well at low surface densities. And so that's what you see in this figure B. At low surface densities, every tridentate new ligand that can come in binds, displaces all the other ones. No problem. But on a much more crowded surface, it's much harder to find for this tridentate ligand. It has to find here a place where there are 3 binding sites available for exchange that are close to each other. And that's why at high surface coverage, these multidentate ligands cannot bind as a multidentate ligand. They have to adapt to the number of available binding sites that are close to each other. And so yes, good to improve the denticity, but be aware that it only works at low surface coverage. And then finally we come to the league of ligands. Which ligand wins in this battle of the ligands? Well, as a very general statement, alcohols are very poor ligands. Amines are better, but not great. You will typically find those 2 in fast exchange. Carboxylic acid, typically tightly bound ligands. Phosphonic acid, one of the best that we have. One exception is for copper. Copper binds extremely well to amines, and you will also find amines tightly bound to copper-based nanocrystals. On quantum dots, I'm adding here phosphines, which are better than amines, but problem with phosphines is that they are air sensitive, so you can only work with them in a glove box. But in principle, they are better because they have a smaller cone angle than these amines. Again, the same order, but here we also have thiols now, which have a very high affinity for those soft Lewis acids like cadmium or mercury or gold. And then thiols bind really well. I'm putting a question mark here because I actually don't really know which one is better, phosphonic acids or thiols. And I'm not really aware of a study that convincingly showed one of the other. So if anybody knows, please send me the paper and I can add it for next time. Then sterics are of course extremely important. Tertiary ligands are poor, secondary better, primary much better. Same for these branched carboxylic acids. It really depends where the branching point is. So the further away from the surface, the better the binding affinity. And then finally, multidentate ligands, yes, are better than regular ligands, but only at low surface densities. Okay. So this was a bit the conclusion of the last section. To summarize the other sections, nanocrystals are not simple colloids. They have an equilibrium solubility that's determined by crystallization of ligands on the nanocrystal surface. Second, binding motifs are helpful to 1, talk about surfaces, 2, predict ligand exchanges, and to kind of generally appreciate the complexity of a nanocrystal surface, while at the same time trying to provide a minimalistic presentation as possible. The NMR toolbox, 1D, DOSY, and NOSY together can tell you a lot about how ligands are interacting with the surface. And finally, the surface is a very heterogeneous place. These NMR resonances are heterogeneously broadened, saying something about the solvation, but also the thermodynamics is very heterogeneous. So be aware, don't just calculate a single equilibrium constant and call it a day.